Okay. All right. Good morning, everyone. We have our next presentation. We'll be talking about what was learned about the stars during our period from about 1700 through the middle of the 19th century. We'll start with this first slide. We'll come to this great behemoth, the Levantine telescope. At the time, the greatest telescope, biggest telescope in the world. We'll come to that in our presentation in due course. But we start again going back to Halley, back in the early 1700s. We began our planetary discoveries with him, and we'll start again with him. He was the second astronomer royal, after all, after Flamsteed, a friend of Newton's, and he not only made great discoveries in terms of his work on the comet, and even other things which we didn't get a chance to mention. But here's a discovery he made, which will turn out to be very important for our story. The fixed stars. Haley found out that the fixed stars weren't fixed after all. He went back to look at the catalogs all the way back to the measurements of Hipparcus and Ptolemy, comparing those measurements of observation of the stars compared to his own, comparing not only his own, but those of the great Tycho. And he noticed that, in fact, the stars were not in the same place. The stars seemed to be moving in the sky. Very, very small amount, to be sure. Going back all the way to Hipparchus to 150 BC, the movement that he saw of the brightest stars, of course, that Hipparchus would be measuring, Sirius, the brightest star, Aldebaran and Arcturus, among the 10 brightest stars in the sky. He saw that the change was about a half a degree in that time. About half a degree, about 1 arc second every year is what he saw on average of these very, very bright stars. So this was quite an amazing and very surprising discovery, that the fixed stars, in fact, are not fixed. They seem fixed, of course, for any generation, even more. After all, moving just a half a degree over such a long period of time, almost 2,000 years, you would not pick that up with your naked eye. It would have to take very detailed observations, but indeed, the stars are moving in the sky. So here's a picture of what the Milky Way looks like now compared to what it'll look like 50,000 years from now. Okay, all the stars are shifting; they're moving in their own direction. Don't know why they're moving in the direction or the speeds that they're moving at, but they are moving, and so the whole shape of the Big Dipper will change very, very slowly over time. Just to give you an example, let's take the star with the greatest, just for fun, let's take the star with the greatest proper motion of about 10¼ arc seconds every year, 10 times more than that average motion that Haley first found of just 1 arc second. Now, this star was not even discovered until the early 20th century, and it was found to be 6 light years away. And knowing the distance it is away and how fast it's moving across our view, we can actually calculate the speed of the star in that direction. Remember, here we are, and we're looking at the star. The star is actually moving in some arbitrary direction at some arbitrary speed. Okay? It has 2 components. One component, it's moving directly away from us, which we cannot measure at all, at least not now anyway. There's no depth perception in the sky. And there's this, what we call the tangential velocity, the velocity across us, across our sweep. That's the proper motion. And we can actually calculate, if we know the distance, we can calculate that tangential velocity. If we know the proper motion, which again, for the Barnard star, the greatest proper motion, about 10¼ arc seconds every year. And if we know the distance, it's about 6 light years away, using the skinny triangle approximation, we can calculate how far across us the star moves in a year. It's a nice little example of these skinny triangle approximation. Here's our approximation here. We put in the numbers that we know. The only number we don't know is little d, the amount of the distance that the star moves across us in a year. We can calculate that to be, comes out to be 1.75 billion miles in 1 year, which is at a rate of 55 miles a second. Okay, so the stars in the sky are moving quickly, certainly compared to any kind of terrestrial speeds that we're used to, 55 miles in a second. Now, this was not a number that Haley knew at the time, because he did not know the distance of any of the stars in the skies. That's probably the centerpiece of our great story of this whole presentation, is to finally calculate the distance to a star. That's going to be another 100 years off from Haley's time. But just wanted to show an example of what these proper motions mean. Although they seem slow to us, in fact, they represent a very great speed, at least a speed across our bow, in a sense, that tangential speed. It only seems slow to us because the stars are so far away. Well, to start our story with Parallax, with the next astronomer royal, James Bradley, who took the post after Haley. And as I said, since the time of Copernicus, right, the great holy grail of all of astronomy was to find that parallax of a star. What Copernicus said, well, what the critics of Copernicus said had to be so. If Copernicus was right and the Earth was going around this great circle of the sun, moving from one side to the other at a great distance, and that distance has only been growing since the time of Copernicus. The distance in Copernicus's time was rather meager, even in terms of these distances here. But we've been tracking the measure of 1 AU, the distance from the Earth to the sun, and we have been getting more and more accurate values as time goes on. I think in the time of Bradley, we're up to about 86 million miles, where the approximate number that we use now is 93. So certainly a good approximation. So with this great motion back and forth on either side of the sun of 86 million miles on either side, don't you think that we would be able to see a parallax? And that was the great criticism, right, they gave to Copernicus. And Copernicus gave the right answer. He says, well, the stars are so far away, we just can't measure the parallax. It's too slight for us to measure. Well, that's a very convenient excuse, maybe, Copernicus, to defend your theory. But in fact, of course, he was right all along. So this was the great holy grail of astronomy, was to find a star close enough that you could measure its parallax. Bradley had a very good idea. There was one very interesting star. He of course, was housed in Greenwich, in London, in the Greenwich Observatory as the Astronomer Royal. And turns out that the star Gamma Draconis, the star in Draco, and the Great Dragon, even though it's called a Gamma star, it's actually the brightest star in the constellation. So it really should be called Alpha Draconis, but its name is Gamma, and Alpha was given to some other star. Just very close in brightness in terms of the naked eye. These things were only sorted out, in more modern times with the real photometers. But anyway, that's the name of the star. And what was interesting about Gamma Draconis was it goes right overhead in London. It is right at the zenith, right directly above your head, looking straight up. This gave Bradley the idea that he could mount a very, very rigid telescope that would not move. He could really rely upon the fact that the telescope would not move straight up. And there's a picture of it here on the right. Here's Bradley's diagram of his design of it, and here is the telescope. Still exists. Where it works here is in the museum now, and it was mounted against the wall of the building. Okay. And you can even see this this pendulum here to measure the angle distance if it was shifted at all from the vertical. And here's how you would observe the star. You'd have to get underneath the telescope to be looking straight up. And Bradley realized that this was an excellent star to use because of the rigidness of the telescope, that we could rely upon the fact that we were always looking in the same direction. And if there was a parallax, if there was a change in the position of the star, it would be because of the change in position of the Earth, not because his telescope was jiggling around so much. The other great thing about looking at a star straight up is you didn't have a refraction problem, right? The light was coming down directly down straight at you through the atmosphere, but it wasn't coming at an angle through the air of the atmosphere. And so the way light works in terms of the laws of refraction, coming straight down through a medium, the light does not bend. So he didn't have to worry about a refraction problem in changing the direction of the star. The star was always directly overhead. So the star had a lot going for it, a lot to say for itself, to look for parallax for Gamma Draconis. And he set up this system of this, he built this telescope for this purpose, made many, many observations. Of course, he was doomed for failure because of right here. The star turns out to be 154 light years away, much, much too far away. The parallax that the star would have would be beyond anything that this technology of this pipe telescope straight up against the wall could possibly detect. But he did not know that. He did not know the distance to the star. He did not know that he was up against something that could never work, that was just something imperceptibly small given his technology. But yet he went ahead and studied the star for a number of years, took many, many measurements, and he found a very, very strange thing. Let's take a look at the diagram of what we're trying to capture. If the star is here and the Earth is going around the sun, then you would expect the maximum parallax to be in these two positions here. When the light is coming in, this is the two sides that we're seeing the light of the star coming at us. And we would get a maximum parallax from these two positions. Here in this picture, it would be in June and in December. Here, when the light is coming straight at us, here we would expect no parallax at all, right? Because we're looking straight at the object. There's no parallax vision from side to see. What Bradley saw, to his amazement, when he took his data, summarized his data, was the exact opposite. Here, where we would expect the maximum parallax, right, in June and December, look what he got in his graph. He got no motion at all, no shift at all in December and in June. He got a zero shift in the view in the telescope. But here, when the light was coming straight on to the Earth, right, here in March and in September, right, September here and March, this is when he got the maximum shift. And it was quite a decent shift. It was 20 arc seconds. Okay? Remember, that's 1/3 of a minute of an arc, and 1 minute is 1/60th of a degree. We're talking about very, very small shifts, right? This is why we're going through such elaborate procedures of mounting telescopes against walls and looking for stars that are straight up. We're trying to eliminate any kind of disturbance that the star's vision would have, its position would have, except for our changing position going around the sun. Everyone knew this was a very, very delicate procedure to do to be successful at. But still, he was getting a decent result, a change of 40 arc seconds from one side to the other, but it was exactly the opposite of when it should be happening. He was getting no change at all when he was in the maximum parallax view, and he was getting that maximum change of 20 arc seconds on either side when he shouldn't have gotten any view at all. Clearly, Bradley realized he was not looking at parallax. This was not a parallax effect. What made it even more intriguing was all the other stars that he could see in his telescope. Yeah, he had a certain field of view, not very big, but there were other stars that he could see besides the star he was focused on, and they all, given the measurements that he took, he would take measurements of the stars in the field of view. They all had this same strange shift. They all had this maximum shift of 20 arc seconds. And this was just a great mystery that the shifting was happening the opposite of parallax. What could be causing this shift? Let's take a look at a picture, a moving picture. I think it might help explain this a little bit better than just this fixed picture. Okay, so let us take a look at what Bradley was expecting to see. What he was expecting to see for parallax was the following. Okay, let's get our bearings. Here's the sun. Here's our blue Earth. Okay, it's going to go around the sun. And here's our star. And as the Earth moves around the sun, we would expect to see the star shift. Now, the star does not move. Okay, we are moving. And because we are moving, what we see is not the star, but we see, of course, the image of the star against the background stars. Okay, and that's the shift that you would see in parallax. Okay, here, when the Earth is straight, when the light coming from the star is straight on, you wouldn't expect any parallax at all. Here, 3 months later, when we're at that maximum distance on the side of the sun, we would expect, if we were going to get a parallax shift, the maximum shift. Again, 3 months later, coming head on, that shift would disappear. And 3 months after that, we would be at the other side of the parallax view, and we would get a maximum shift on the other side. And this is what Bradley was expecting to see in his data if he was going to have Gamma Draconius show a parallax shift. He did not see this. He saw the exact opposite. Let's take a look at that. What he saw, to his great surprise, was this, that when the light was coming straight in at him, at the Earth moving in this direction, that's when he saw the maximum shift. And the shift, in fact, was in the direction of the moving Earth. And at one of the maximum parallax views, looking to the side, he saw no shift at all. Again, the shift grew and grew until when the Earth was moving, across the bow of the star, across the bow of the light coming from the star, when the Earth was the Earth's motion was perpendicular to the to the light coming in from the star, that's when he got the maximum shift. So clearly, this was not a parallax. It was happening in the exact opposite of parallax. There was his maximum shift, when the parallax should be at zero. Here's when the shift was at zero, when he was at the optimum parallax view, the exact opposite. This is what he saw. Not only did he see this for the star that he was studying in very closely with all the meticulous data that he took, he also noticed this for the other stars that he could take measurements for in that field of view. They were all doing the same thing. Clearly, this was not a parallax effect, because certainly you can't assume that all the stars in the view of his telescope all had the same distance. That would make no sense. The individual stars would be at individual distances. They would have different parallaxes, but yet they all showed this 20 arc second shift back and forth in the opposite behavior that you would expect for a parallax. What to do? What to make of this very strange situation? Well, the story goes that he was out pleasure boating on the Thames one day with a party of friends, and he was sitting on the boat watching the flag on the mast. And as the boat went back and forth on the Thames, tacking back and forth, he noticed that, of course, the flag was always pointing in the direction opposite of the direction of the boat. We, of course, all recognize this thing. If you're ever on a bike, no matter even if it's a very calm day, if you're going at a decent speed, you will get a wind in your face, no matter what direction the bike is heading. If it's a calm day, you will always feel the wind in your face. Bradley realized that that's what he was looking at, that it was the motion of the boat that was creating the effect on the flag. Another analogy that's often given, that's often done in a high school physics class, is we think of a rainstorm, again with no wind. Well, the rain comes straight down. If you start walking, or in fact, if you start running, and if you don't tip your umbrella, you're going to get wet. The front of you is going to get wet because of your motion, the rain is still coming straight down, but because you're moving quickly, the rain seems to be coming at an angle. And that's what Bradley realized what was going on. It was the motion of the Earth that was causing that shift. And it was clear once he saw that because when the Earth was moving in one direction against the motion of the light of the star coming in that perpendicular direction, just as we have the runner moving perpendicular to the direction of the raindrops, that's when the shift was, towards his motion, just as this rain is coming towards his motion. He saw the exact analogy that it was the motion of the Earth that was creating this shift back and forth. Indeed, it was not a parallax shift. And in fact, if you want to, given the speed of your running, if you want to not get wet at all, you have to tip your umbrella at a certain angle to match the incoming direction of the rain. Bradley realized that if you don't tip your telescope a certain amount, then the light coming from the star will be tipped and not be in the center of the telescope. It's very, very small. It's very, very tiny, but that's in fact what he was seeing. Again, a picture may help, but before we do the picture, let's just take a look at that telescope view one more time. If the star is coming in and the telescope is moving, the telescope is on the Earth, and the motion of the Earth is not nothing, it's pretty fast going around the sun. Nothing compared to the speed of light, I grant you, but it is a decent speed. And since the telescope is moving, if you want to get the light of the star in the center of your field of view, you're going to have to tip that telescope down. Otherwise, you're going to get a shift away from the center of the field of view. Okay, and that shift he found to be at a maximum 20 arc seconds. Again, I think a picture will help. Okay. So here we have our telescope that is moving, and here's the star, and the light comes down from the star, and of course the telescope is moving all the time. It's mounted on the Earth, straight up on Bradley's wall, and as the light enters the telescope still moves, and so the path of the light looks like that. Okay, because of the motion of the Earth, the light does not come into the center of the view of the telescope. It's off center. And since our eye, whether we're looking at it as an eye or in a camera, we always follow the path of the light back from the path of the light. We always see the light coming from the direction that the path of the light took. And this is actually the path that the light took, right? This dotted red line. And so it looks like it's coming from this direction here. And there's that forward shift. The shift, here's the real position of the star. Here's the forward position because of the forward motion of the Earth. And that maximum shift, again, is 20 arc seconds. Should we look at it one more time? The light comes down to our moving telescope. It continues to move as the light goes through. And so we have the light coming off center, looking like the star has been shifted. Now you may say, my goodness, the speed of light is so fast that this just takes an instant to go through his measly little telescope. The Earth really is moving that much? Yeah, well, it's only 20 arc seconds. 20 arc seconds is not much, okay? But yes, apparently this was enough to pick up this shift. So let's take a look at the math and see just what that is. So sure enough, we have another skinny triangle, right? 20 arc seconds is a pretty skinny angle. So the Earth will move at a distance vt, where v is the speed of the Earth. We can calculate that. And the distance down will be the distance ct, where c is the traditional speed of light that we always use. Okay, and that's capital D. And sure enough, we have a very skinny triangle. Of course, not to scale. This is only 20 arc seconds in here. And yes, we do have a very nice skinny triangle. We have the 20 arc seconds over our funny number, 206,000, is to little v is to big D. Little d is the speed of the Earth times the time it takes to move through the telescope. That's how far the Earth moves in that time. And this is how far the light goes, basically the length of the telescope, CT. Notice that the t's cancel out. Doesn't matter really how quickly this happens. It's the same ratio as the velocities of the Earth compared to the velocity of light. But Bradley can calculate the velocity of the Earth. That's pretty simple. The velocity is simply the circumference over the period. It's the total circle that we make around the sun divided by 1 year and seconds. A lot of arithmetic. Here's his notion at Bradley's time. The distance of 1 AU is 89 million miles. Pretty good approximation. And so this is the speed that he got for the Earth. Not too shabby. 17.7 miles per second. Yes, nothing compared to the speed of light, but then again, 20 arc seconds isn't much either. And so therefore he can solve for C, given that 20 arc seconds. And he gets a value of 182.5 miles per second. That is 98% accurate to our modern value. Famous speed, the speed of light is 186,000 miles per second. He got 182,500. Remarkable, right? In 1732. It is so interesting that here we come to the second calculation of the speed of light, again done by an astronomer. The first one done by Ole Römer, if you remember, last term, by looking at the moons of Jupiter, looking at Io, how it changed its eclipse time, how long time it took to come around from the back of Jupiter, and measuring that delay, that increasing delay, realizing what he was looking at was the delay it takes for the light to get across the orbit of the Earth, going around the sun. I think, if I remember, I think he was 66% accurate, if I remember correctly, something in that neighborhood. Well, now we come about 100 years later, not even so much, maybe 70 years later, and we get a value of the speed of light of 98% of the modern value, again done by an astronomer. Quite remarkable to think that it's going to take over 100 years from here, from Bradley's time, before the engineers will figure out something clever enough. We'll get a clever enough engineer to figure out how to measure the speed of light in a lab here on Earth. Until then, 100 years in the future, it is the purview of the astronomers who can work with great distances or very, very tiny angles to make calculations like this. So this is a very impressive feat and a great accomplishment at this time. Notice also, by the way, just for fun, Bradley, of course, has proven that the Earth moves. This whole phenomenon is happening because the Earth is moving. So wouldn't Galileo have been happy with this result? Okay, that we finally have the first empirical proof that the Earth, in fact, does move, moving around the sun at quite a good speed. Of course, we know that it'll take over 100 years to get the first empirical proof that the Earth is spinning, and that's the Foucault pendulum. Hopefully, everyone has seen that from a science museum that you visited at some point, where the pendulum swings back and forth, changing its orientation because the Earth is spinning on its axis. That's 100 years in the future of Bradley's time. One other thing that Bradley accomplished, he says, well, I was not successful in finding parallax with my star, but I know I could have picked up a parallax, an angle P, of 1 arc second. If there was a change in 1 arc second at those two extreme points where I wasn't getting anything, I would have seen 1 arc second, and I didn't see anything. So how far away must Gamma Draconius be? Well, let's see how far it would be if, in fact, he did see 1 arc second. Okay, what would the skinny triangle approximation be? Well, again, we write down our skinny approximation, where now p is 1 arc second. Our little d here is 2 AU. Okay, and here's our capital distance d. Okay? This would be the relationship if he had seen a parallax of 1 arc second, which he didn't. So therefore, this d that we're going to calculate is less than the true d of the star, because he didn't see, he saw something smaller than whatever parallax there was, if there was any, was less than 1 arc second. But 1 arc second would have given you 400,000 AUs, 6.4 light years. If the star was that close or closer, I would have gotten a parallax of 1 arc second or larger, but I didn't get it. Therefore, the star must be further away than 400,000 AU, is what Bradley was able to conclude. Okay, not a speculation. He can conclude that Gamma Draco is more than 400,000 AU away from the Earth. This is a time when the largest distance we know before then is 40 AU. Remember, that's the aphelion of Halley's Comet, the furthest measured distance that we have. That Halley's Comet swings out a distance of 40 AU from the sun before it turns around and starts to come back in. Bradley has made this 10,000 times greater. Okay? He knows that the stars, at least Gamma Draco and all the other stars that he could see in his view, were at least 10,000 times further away than Halley's Comet gets at its further distance. We can see what the effects of the scientific revolution, the technology of the telescope as it gets more powerful. We can see that we're just in front of our eyes, we're beginning to move into the modern age. Okay, we're beginning to understand the dimensions of the universe. You can imagine how overwhelming that these distances were at the time of their discovery, of their confirmation. And I can't emphasize enough, there's always been philosophical and poetic speculations about all these things. These are scientists, okay, coming up with hard numbers from hard measurements. Very, very different quality of information. Okay, let us now talk about Herschel. Okay. I said last time that he is by far, going away, the most important astronomer of the 18th century, of the 1700s. We've already seen one of his accomplishments, that is of discovering the planet Uranus. I think you'll agree with me when we finish these few slides that that was probably one of his least important discoveries. He, of course, would be in the history books if he had only done that. Okay, but let us look at so much more that Herschel discovered with his great, powerful reflector telescopes. Right? He was an amateur astronomer, remember. Okay, he was not a professional. He was not interested in finding the next decimal point for the orbit of Jupiter, or Venus, and checking that with Newton's laws to see that he was not interested. It's not interesting to an amateur. Be looking at the 5th decimal place of some calculation of celestial mechanics. Okay, he was interested in discovering new things. He wanted to see things which were very, very faint, that couldn't be seen with other telescopes, that were very, very far away, that were never seen before. Yeah, he had this amateur ambition to find out things new. And this was a very different point of view from professional astronomers. Professional astronomy was all about the planets. It was all about finding new comets. That was a big, big deal. Measuring in more and more greater detail the orbits of the planets using Newton's mechanics. Okay, This is, of course, how Neptune was found, right? By doing those detailed calculations on Uranus once it was discovered, and then making a backwards calculation to see what could be disturbing that. This is what professional astronomers were doing. Herschel had no interest in this. He wanted to discover things that people had never seen before. What he said was he wanted to understand the whole construction of the universe. That was his goal. He didn't realize as an amateur how crazy that goal was, how beyond the technology and the abilities of astronomy at that time. At least that would be the opinion of the professional astronomers. It was just a hopeless goal to have. During his life, Herschel and his sister Caroline made many what they would call sweeps of the entire sky, what he could see from his backyard in England, using more and more powerful telescopes. This is his second most powerful telescope. This is a 20-footer with a mirror of 18 inches, and this is literally where he had to sit. This is where the eyepiece was. This was the design. The mirror, of course, is way down here, and the light would come in from the star, bounce off of the 18-inch mirror, and come back up here, focused here at the eyepiece, and this is where he sat. Caroline would sit down here with candles or a lantern or whatever, and he would be calling out stars and their position in the sky with respect to the telescope, and Caroline would write down those positions and the time that her brother would call those out. And between position and time, that's how astronomers get an accurate overall position of the star in the sky, in the starry vault. And they would do this night after night after night. No one knows how they slept and when they slept, because certainly for a few years they were still both professional musicians. Caroline apparently had a beautiful voice, and one of the first things William did when he brought Caroline over was to start giving her voice lessons, and she began giving concerts in Bath. He, of course, was the overall music director, and organist, and composer, and she became his primary lead singer. How they had their musical career during the day. Also during the day, he began building mirrors and building telescopes, and then they would do observations virtually all night. And this is what they did for years and years, amassing catalogs of different sorts that stayed in modern catalogs until a whole other round of telescopes would make them obsolete, maybe in the order of 50 years later. So the first discovery after we talked about discovery of Uranus. It was interesting. Herschel said, well, we know that the stars are moving through the sky. They have a proper motion. They aren't fixed. Well, what about the sun? The sun is a star. Is the sun moving through space? We're a long way now from Copernicus, where the sun was the center of the universe. Herschel is now contemplating the sun moving through space. And he, with all of his catalog measurements, his vast data of measurements of the stars, looking at those positions over time, he saw that, yes, the stars did have proper motion. He could see that comparing his catalogs with Flamstein's catalogs, with Tycho's catalogs, with he could see that there was clearly motion, but it wasn't completely random. It wasn't like a bunch of gnats flying around in the sky. There was some kind of a drift to the stars as we view them from the Earth, and it looked like this. Okay, a famous picture from Star Wars, that as the ship moved into warp speed, shooting through the fixed stars, what it would look like to us is exactly like this. If you ever were running through the woods where the woods were all the trees were all planted in a very, very even way. If you ran through the woods, the trees would come at you like this. They would move away from you in a circle. That's if you were moving towards this uniform distribution of objects. If you're moving away from it, then it looked like the circle was collapsing behind you, right? So the people who made Star Wars got this image very, very nicely done. This is what Herschel saw in his data. Of course, clearly not as dramatic as this, but this is what he saw. He saw this kind of general motion of all the stars with their random proper motion had a bias, a drift like this. And here's his diagram of the data explaining this, which we now call the solar apex. And what he saw was that the sun, the Earth carrying along with it, was moving in a certain direction. If we think of this as the starry vault, the original starry vault, which we still have, of course, still used for navigation, of course. But the sun was moving in a certain direction in that starry vault. And he was able to locate it here within the beautiful summer triangle, just below Vega. The summer triangle will be coming out for our views soon. It'll be out all summer. The three great stars of Vega, Deneb, and Altair. Deneb being the brightest star in the Swan. I don't know if you can see the Swan. Here's the tail, here's the wingspan, and here's the head of this great Swan. And so here's where Herschel located what we now call the solar apex, the direction in which the sun seems to be moving in the sky. Okay. A wonderful discovery of Herschel. If he had only done this, he would be in the history books. But there was so much more. He, of course, also was interested in parallax. Yes, he caught the parallax bug as well. Even as an amateur, he appreciated the importance of finally finding the parallax of a star, what that would mean. It was no longer necessary to find the parallax of a star to prove that the Earth was moving. No one needed to prove the Copernican paradigm anymore. Newton's laws and the tremendous accuracy of the motion of the planets showed that to be the case. Bradley with his, by the way, I don't think I gave the name, it's called the aberration of light, of starlight is the name that's given to that shift, that opposite shift from the parallax. The aberration of life shows that the Earth is moving. No, this parallax was not about proving that the Earth was moving anymore, moving around the sun. This was to measure the distance to a star, to finally begin to put together, as Herschel said, the construction of the universe. And you really couldn't get started with that, not in great earnest, until you began to measure the distance to stars. Galileo pointed the way in the great dialogue, the two chief world systems. He discussed how you would find parallax, a good way to do it. He says, take a look for double stars. Take a look in the sky for two stars which seem very, very close together. They're not. They just look very close together, one the far star behind the other. But through your telescope, they look like they're very, very close together. Why would this be a great advantage? Well, from looking from the two different opposite sides of the orbit, you would potentially, you're supposed to see the close star from two different points of view. It would have two different places in the sky. And instead of trying to measure things from baselines, which we can't even see, the baseline from the Earth to the sun, we would have a reference star to measure from. This far, far star, okay, which is directly behind our star, but if it's very, very far away, this will have no parallax, okay, because it is so far away. This will truly be a fixed star compared to our motion here going back and forth around the sun. We would have two sightings, okay, let's say in January and June, okay, to make things simple. We would have two sightings of our close star, and we could measure them with respect to the fixed star. It'd be much easier to measure this angular separation here than anything else. This was Galileo's suggestion as to what to do. An excellent suggestion. And so therefore, to find double stars, to find candidates where one star is close and one star is far. How do you do that when you don't know any distances? Well, you gotta make the best you can. First of all, you have to find the double stars, and then see if you can find some candidates among those double stars which could fit this kind of a bill, where you would have evidence that one star was much further back behind the other star, even though they were very close in the sky. That was the idea. And so Herschel began to make a catalog of double stars. And before long, he had a catalog of 800. They were actually called binary stars. And the stars that Galileo was asking them to look for was which we call optical binary stars. They just look like they're close together. They're not really. That's what Galileo wanted to find. Find optical ones. Don't find stars which are really close together. That's worthless in terms of parallax. Okay, you're not going to get a parallax shift with two stars which are very close together. You got to find stars which are only optically a double star. Okay. Oh well, here's a nice example of one. Albireo, another star in the Swan. Okay, it is considered the head of the Swan. Deneb is the brightest star, the tail. Here's our wingspan. So Albireo is inside the summit triangle, and this is a very pretty double star. You don't see this with your naked eye. Okay, you need a telescope to see this. And this is just an example of a true optical binary star. These two stars are not close together. Okay, the one star is much further away than the other star. And what you would think, you know, in Herschel's time, around 1800, what you would think is, well, the bright star is closer and the dimmest star is further away. What else do you have to go on? So what you'd be hoping for, if you were to study this star night after night, year after year, studying, taking the most accurate measurements you can, you would hope to see if you could get a shift of the bright star with respect to the background dim star. That's what you would hope. Okay? No guarantee that the parallax would show up, no guarantee that your instruments are sensitive enough, no guarantee that you really do have a close star and a bright star, no guarantee of anything. You just have to find candidates, take measurements, take a look at your data as it accumulates over the years. Astronomy is a very patient science. If you are not a patient person, you do not want to be an astronomer. Well, so what are we looking for? We're looking for stars which are close. What's a close star? What can you go with at this time when no one knows the distance of any star? Well, bright stars are a good candidate. If they're bright, maybe they're close. Not bad. If you don't know anything else, the brighter the star, the closer it would be. And also their proper motion. Yeah, if they have a high proper motion, if they're moving across us very quickly compared to other stars, they could be close. Okay, they could be moving very fast. Yes, that's true. But if all the stars are kind of moving around the same speed, if there's no reason why one star would be truly moving in space much faster than the other stars. Are they all kind of moving in the same average speed for some reason? Then the ones with the higher proper motion would be the closest stars. So these would be your candidates. Turns out that James Bradley found one. He found a nice double star called 61 Cygni. Again, we're still in the Swan. Okay? And here's Cygnus, the Swan. And here again is the constellation of the Swan with the tail and the head. And here is 61 Cygni. Not a very bright star at all. But it was of interest because at first it was a double star. By the way, 61 comes from the Flamsteed, the first astronomer royal. His catalog, it was simply moving from, I think, east to west, I believe. You just start counting stars in the constellation, and this is the 61st star that you count, moving in one direction, and that's where it gets its name, 61 Cygni, the 61st star of the Swan. So it was a star that was recognized as a nice double star. Herschel took a look at it, found it very interesting, and He studied it and studied it, and he identified again hundreds of many of these stars. Bradley realized that it was in fact a double star, okay, and that's what piqued his interest. Herschel studied it and also, of course, accumulated many other binary stars, whether they were optical or visual. First thing you see is that they're optically close. And Father Piazzi noticed something very interesting, nice attribute of our star. It had a very, very high proper motion. Remember Father Piazzi from Palermo? He's the one who discovered the first asteroid, Sirius. Okay, so he, in his measurements, had discovered that yes, it has a very nice high proper motion. Okay, so a candidate to look at among many, but this star will play a very important role in our story. 61 Cygni. Okay, but going back to Herschel. Herschel and making a catalog of all these binary stars and looking at them year after year, going back and checking their positions compared to when he first saw them, and any other catalog positions that he could find. Of course, his catalog of binary stars was 2, 3, 4 times bigger than any previous catalog. He could see stars that no one could see. The astronomers of his day, the professional astronomers of his day, did not have the power of the telescopes that he was building. They were using lens telescopes of relatively small aperture, 5, 6, 7, 8 inches of aperture, very, very fine quality lenses that you could take accurate measurements of planets. Look for comets in the solar system. That's what the great interest was. They could not see what Herschel could see with his 10, 12, 18-inch mirrors, okay? And what Herschel discovered when he went back and looked at his binary stars, that in fact, yes, they were moving. They were shifting. Many of them were shifting, but they were shifting with respect to each other in a way that suggested that they were bound gravitationally. They were moving around each other. They were moving just the way Newton said they would move if they were locked in a gravitational embrace. They were moving they were both orbiting around their common center of mass. And this was first discovered by Herschel. Okay. It was finally confirmed a little bit later in 1827 at the Paris Observatory by one of the astronomers, one of the theoretical astronomers, Felix Savary, who showed that, in fact, yes, these orbits were, in fact, Kepler's elliptical orbits, according to Newton's laws. But Herschel is the one who first saw this, who took the data, and who made this prediction, okay, that we were looking at the universal law of gravity for the first time outside of the solar system. Another incredible discovery by Herschel with his catalog of binary stars. These are now called visual binaries. Optical binaries are stars which aren't close together, they just look close together in the sky. Visual binaries, of course, are stars that look close together because they really are close together. And if you're patient enough and are accurate enough in your measurements, you can confirm that, in fact, these stars are orbiting each other around the common center of mass. Okay. Another set of objects that Herschel was interested in were the nebulae. Many nebula. Nebulae, I think, is the proper plural. They're just balls of, white, misty stuff in the sky. Clearly bigger than a star, bigger even than a planet when you look at it through the telescope. Sometimes, and it was this kind of milky white circular substance. Well, as I mentioned, comet hunting was the great indoor sport, or I guess I call it the outdoor sport of astronomers. This was the most exciting thing, was to discover new comets. Remember, Caroline was a great comet hunter. She found 7 or 8 comets on her own. among her many accomplishments. But the great comet hunter of the time was a Frenchman by the name of Charles Messier. And he was annoyed because of these nebula, that when you would first see them through the telescope, you would say, oh, maybe that's a comet. And you'd have to watch it for days and days, night after night, and realize, oh, this thing is not moving. This is not a comet. This is one of those nebula. So just to clear up the situation, he made a catalog of these things. These were nuisances to him. He published this catalog of nebula to tell all of his comet hunting friends, don't bother with these guys. These guys are not comets. Don't be fooled by them. They're just milky white circular blobs of God knows what, but they're not comets, so they're of no interest to us. Well, Herschel, again, being Herschel, he thought that was very interesting. He wanted to know what these funny things were. Okay, they weren't comets. Well, what were they, after all? So he set about going through Messier's catalog. By the way, this is probably the most famous catalog of objects for amateur astronomers. If there are any amateur astronomers hearing my voice right now, you are smiling at of course, the famous and the importance of the Messier Catalogue. And one is the Great Crab Nebula, and probably the most famous of all is M31, which is the Andromeda Galaxy. These, of course, were not known. They were just circular, milky white, hazy gray things in the telescope that weren't moving, and therefore they weren't comets. Okay, but these are among the most famous and the most looked at objects by amateur astronomers. They're such fun to look at. With modern telescopes, you can begin to discern what they really are. Well, Herschel began looking at all of these nebula in the existing catalog, and not surprisingly, he found a lot more. He found like 1,000 more of these things that were in Messier's original catalog. He found all kinds. He found 1,000. Then he found 1,500 more after that. Again, because of the incredible power of his telescope. And he began to categorize what they were. Okay, they were open clusters, clearly that you could easily resolve them into stars, the most famous being the Pleiades. Then a word that he coined, global clusters. These were very, very dense, just through a normal telescope of the day, not his. It was just like this kind of milky blob. But through his telescope, he could resolve many of them, not all of them, but he could resolve many of them into a myriad of stars, kind of in the thickness, the density of the Milky Way. And he called these global clusters. Here's M15, for example, in the original Messier Catalogue. And here is just a picture, drawing of Herschel, of the different kinds of nebula that he found. And we don't know where this comes from, but he had the idea that what he's looking at is almost like an evolution of these clusters, that they form in some way. They all were, collections, clusters of stars, and they would begin to form in some way and evolve and become denser and denser and denser. And becoming so dense, he predicted at some point that these things would collapse under their powerful mutual gravitational force, that this whole thing would collapse into some kind of an explosion, and the stars would be all destroyed and dissipated out into space in order for this thing to start all over again. Herschel had this idea that was not at all in the air, not at all a common idea, that the universe was an evolving entity, that the objects in the universe were changing all the time, that there was an evolution to the things that you can see. He even suggested the way to do this is to study as many categories of an object that you're interested as you could find. And you would see them at different stages of their evolution, just like these global clusters. So he had this notion of an evolving universe ahead of the professional astronomers. incredibly, as we know, important idea going forward, leading ultimately to the Big Bang. So what were these clusters after all, these global clusters, these nebula? Herschel went back and forth. At first he thought maybe they were all just clusters of stars. Some he could resolve and some he couldn't. The ones that he couldn't resolve, he realized these things have to be very, very far away. They're big. They're big in the sky and they're bright enough that I can see them, but yet I can't resolve them. So if they are stars, this cluster must be incredibly far away. This must be like another Milky Way. And the idea of the island universes are born in the idea of Herschel. We now call them galaxies. Okay? They were called island universes at the time. That some of these clusters of stars, this nebula, were in fact a world of stars in itself, very, very far away from any of the close stars that that we see in the telescope. Again, the imagination to expand the universe beyond what the professional astronomers of his day in around 1800, their view of the universe compared to what Herschel was thinking about. This amateur, the greatest astronomer of his day, of his time. And then, as luck would have it, or inevitably, he found a nebula which was very strange. In his observation book, he called it a most singular phenomenon. It was a cluster. It was a nebula. It was a blob. Because he didn't see it as blue. This is a modern picture. But it was a blob, but it had a star in the center. And the rest of it he could not resolve. This clearly was not a cluster of stars. He called this a planetary nebula. We call them the same today. Okay. He didn't know what it was, but he knew it was not a cluster of stars. So he had to back off from his speculation that all nebula were clusters of stars. This was something else again. This was a singular phenomenon, as he called it. And what he thought it may have been would be a star which hadn't fully formed yet. And the cloud around it was still being pulled in by the star by gravitational collapse to become finally a normal star that we think of as a star. That was his idea of what a planetary nebula was. It's not. It's something else. But that's way outside of our story. But he did discover the planetary nebula and took a stab at what they were. And the last thing, with all of his observations and all of his data, the best that he had in terms of distance was brightness was close, dimness was far. And in looking at his catalogs, this is the shape of the Milky Way that he came up with by looking at dimness is distance. Not so bad, huh? We have here the sun, the earth in the center, and this was the basic shape that he could find, he could ascertain. It was a disc-like shape. It was a flat kind of shape. For his time, this again is a remarkable achievement. And I think we have a chat question? I don't have one up. I'm sorry, I thought I saw something flashing. There is a chat. I have a chat of 2. Okay, that's all right. Jim's got to run. Okay. Yeah, Herschel. Let's go through it. Discovery of the planet Uranus. He really transformed the whole field of astronomy from what the professional astronomers were obsessed about to the construction of the heavens. He made good on his goal. He established Newton's laws beyond the solar system. He established the motion of the whole solar system through the stars. He argued that the nebula were in fact dense clusters of unresolved stars, or they were stars in formation. He established that the Milky Way was a flat disk-like collection of stars and nebula. He held that the universe was continually evolving according to nature's laws. It was not a static thing at all. That the objects, the great objects of the universe, were evolving and changing all the time. He discovered infrared light. We'll see that in our next presentation, our final presentation. He built the largest telescopes in the world, and he built catalogs of stars and nebula, which again lasted, for a long, long time as the authority of what these objects were. I must tell you one funny story. We remember Cavendish, the great experimental physicist, the one who measured capital G, called weighing the Earth. There's a story that Herschel's son, John, a great scientist of the 18th century, in his own right, very, very important scientist, John Herschel. He tells a story that his father was at dinner one evening, very fancy, posh upper class English dinner you can imagine, like in the movies. And Herschel is sitting next to Cavendish. Cavendish, by the way, didn't get out much. He never married. He was a real hermit, independently wealthy, lived in his own castle. All of his experiments were done in his castle. Really eccentric kind of guy, but a brilliant experimental scientist. John Herschel tells a story that they're sitting together at dinner, not saying a word. One of the speculations, or one of the claims that Herschel made early on, was that he could resolve a star into his circle like a planet. Not true. He got carried away with his seeing. He thought he could see what, in fact, what he wanted to see. But it was a remarkable thing to say. Astronomers were very, very skeptical because the stars were so far away that even Herschel's telescope could not resolve a star into an actual disk. That would not be done, by the way, until really the last 20 years. That was finally done with the very, very large stars like Betelgeuse. But anyway, Herschel claimed that he could do this. And so the story that John tells, his son tells, is that there they are sitting at dinner, not saying a word to each other. And at one point, Cavendish turns to Herschel and says, "I'm told that you can see stars round, Dr. Herschel." Herschel replied, "Round as a button." Nothing more was said, as John tells the story, until they were leaving. Cavendish asked, "Round as a button?" And Herschel replied, "Exactly, round as a button." That is the entire exchange between the greatest experimental scientist of his day and the greatest astronomer of his day. So talk about English, whatever. Okay. So the controversy of the nebulae continued on. It was one of the great unresolved questions. What were these things? And an Irishman living in the Dublin area, independently wealthy, name of William Parsons, later became the Earl of Rose. He wanted to build himself even a bigger telescope than Herschel. Herschel showed the way. Herschel showed how to build these great mirror telescopes. And in 1845, he first of all built a 30-inch telescope, and then he built his 6-foot, his 72-inch telescope, called the Levanthian of Parsons. Still exists. There it is. There's a photograph of it. Of course, it's not used. It's just a museum today. But he built these large telescopes to resolve the nebula question. Could you resolve all of the nebula into stars, as Herschel had once thought, or were some of these nebulae fundamentally different? They were not clusters of stars. They were something else. And he was going to decide this by building this 6-foot wide mirror telescope, 54 inches long in the focal length. And here's, with his 36-inch telescope, here is his exposure of the Crab Nebula. Okay, this is M1. Not bad. This is, of course, before photography, so you draw on a sketch pad where you're sitting at the telescope with a sketch pad in your lap, and you're drawing what you see. Here's a photographic exposure around the turn of the century, and here's the Hubble picture of the Crab Nebula. And he couldn't really tell what this was. He couldn't tell, kind of had a graininess to it. Maybe they were stars, wasn't clear, okay? We now know that the Crab Nebula, of course, is the remnant of a supernova. Probably most importantly, what Parson was able to do is to resolve another nebula, which we now call the Whirlpool Galaxy, called M51, still called M51. He went, through Messier's Catalogue, of course, looking at the nebula, and he was able to draw this picture of M51. He was able to resolve this thing into stars in this kind of circular spiral kind of construction. The first time a nebula was seen like this. Here's again a picture in the turn of the century in the early photography work. So not bad. His drawing, not bad compared to the picture of 1899. And so he seemed to be a believer that yes, all nebula should be, with a powerful enough telescope, could be resolved into stars. What about the planetary nebula? Well, he didn't know, but he thought that through telescopes like his, the issue could be resolved, that all the nebula would be ultimately resolved to be merely clusters of stars. Whether they were close or far away, of course, was another story, but they all were fundamentally the same thing. And here again is a modern picture, a Hubble picture of the Whirlpool Galaxy. Again, these were not galaxies at the time, they were just nebula. Herschel would say, well, when you look at something like this, it is so bright, it is so large, but yet if it can't be resolved in my telescope, it must be so far away. So if this is a cluster of stars, it must be its own universe. It must be its own Milky Way type construction. And then when you see these spirals, this flat kind of spiral kind of figure, kind of reminiscent of Herschel's picture of the Milky Way structure, certainly very suggestive that these are perhaps island universes. Not to be resolved, the question until the 20th century. Okay, we're going to stop here. We have a few minutes to go. We can stop here because we now enter into the second part of our discussion. This is just where I wanted to stop, where we would talk about Bessel and von Struve, the two great astronomers of the middle of the 18th century, who found the parallax of a star. These are the guys who invented precise astronomy, the techniques that they pioneered, the telescopes that they used, the mathematical procedures that they used, the way they reduced their data, taking raw data and taking out the refraction and taking out the aberration of light and taking out the change in temperatures and everything else that could affect their measurements to finally come up with just what was left was just a parallax. All those techniques of the telescope, those mathematical techniques of cleaning the data, was all pioneered by these two men. And we'll wait to tell their story next time, to come to the great measurement of the parallax of a star for the first time. And once that starts, once we begin to know the distance to stars, once that threshold is crossed, we truly begin to move into modern astronomy, that you can begin to construct what the universe is like. You can begin to tell which stars are actually brighter than other stars. You can begin to measure their brightness objectively, because we know what their brightness looks like, their apparent brightness, and we know their distance. And from that, as we'll see next time, we can begin to measure stars' brightness compared to, for example, the brightness of the sun, and all kinds of things like that. Okay, guys, so that's it. Let me go ahead and unmute everybody. So as you leave, I'm going to unmute everyone. And that is our class. If there are any questions as you guys are leaving, please just speak up. Any questions from anybody?
Peter, are you going to do a seminar on Monday morning?
Yes, we're going to do a seminar, and you are very much invited. Who are you?
Pam.
Pam.
Blair.
Okay, Pam. Yes, please. Everyone who wants to come, please get a chance to get to know your fellow students, talk about yourself. That's always fun. A little bit of your background and your interest in science and anything else about the course or anything else like that. It's a kind of a fun time. People who come enjoy it. Doesn't last for more than an hour. So if you're free on Monday morning, I'll be here, same time, same station. All right. If there are no other questions, guys,
I have a question.
Yes, question.
Yeah. Going back to the early slides about the where Bradley failed to discover parallax.
Yes.
Okay, you showed us where there was a shift, and that was when the Earth was going at right angles.
Yes.
The star.
Just exactly opposite of what you would expect for parallax.
Right. And then where you would expect it, there was zero shift.
Correct.
Yes.
That's because the star was 154 light years away, much too far away to detect any real parallax.
Okay. What I want to know is what was he seeing between those 2 points?
Oh, the shift would be continuous, going from 0 up to 20 arc seconds, back to 0, 20 arc seconds the other way, back to 0. That graph that you'll see in that slide, that's the graph of his data.
Okay, thank you.
All right, guys, any other questions? All right, have a good week, everybody.
Thank you, you too.
Okay, bye-bye.
Thank you. Bye.